Okay, thank you so much. Hello, everyone, and welcome to this online webinar of the fundamental aspects of water flood. I'm Hisham Mukhtar, Senior Reservoir Engineer from Cairo, Egypt. So, in today's session, I'm going to talk about the fundamental aspects and principles and applications of water injection or water flooding. Before starting, I'd like to take this opportunity to express my support for all people around the world amid the COVID-19 outbreak. Our hearts and prayers for all people in this outbreak, and a special support for the medical staff around the world. Right now, I'd like to start directly with our agenda today. Introduction with the water injection. What is the water flood? How does it work? The value of water flooding or water injection throughout the field operations, different geological aspects of water flood. What are the important reservoir rock properties related to water flooding? The definition of reservoir heterogeneity and the permeability variations. And after that, we will define very important fundamentals related to water injection operations, mobility and mobility ratio, voidage replacement and recovery process. After that, the fundamentals of the immiscible displacement process, and next is the performance analysis and surveillance of water flood and optimization, and finally the case study for water injection. So now, as background, I'd like to define what is the reservoir engineering. Reservoir engineering is typically a branch of petroleum engineering that's related to the fundamentals of fluid flow in the porous media during the development and production of oil and gas fields. The main objective of this subject is to achieve the ultimate economic recovery. The typical activities of water engineering, as you know, is to know how much oil and gas is originally in place, how much oil is recoverable, what are the reservoir deriving mechanisms, how the future production profiles, and how to increase the reservoir ultimate recovery, how to implement water injection or even gas injection operation. So the water flooding is the most widely used technique for improving or recovery. The operations of water flood recognized in 1990 as a mechanism of oil recovery. The enhanced oil recovery techniques started typically in field operation from 19th. Fieldwide applications started in 1930, and worldwide engineering applications of water flood started in 1950s. Typically, the water flood is the injection or the improving the reservoir or the oil recovery by injecting water as immiscible displacement process. Typically, in oil fields, we have natural, what we can call the natural water influx, which means we have water aquifers. In this case, the we have water influx from the aquifer water. This influx will support the reservoir pressure. With the any depletion in the average reservoir pressure, and also dependent of the strength of the aquifer. At first, I'd like to highlight the difference between primary, secondary, and tertiary recovery operations. Primary is typically based on the natural reservoir energy, like the solution, different sources of reservoir energy, like expansion and release of solution gas, influx of aquifer water, the expansion of gas cap, and so on. So the primary recovery is typically recovers up to 30% of the original oil in place. In this case, the production may be natural flow without any supplement in the wellbore or even the artificial lift. The secondary recovery technique is the applications of the immiscible displacement process, like water injection or water flooding operation and gas injection operation. The estimated oil recovery is from 30 to 50% of the original oil in place. And the third part is the tertiary recovery or enhanced oil recovery. In this case, we have different techniques that works to change some reservoir rock or fluid forwards, like the thermal operations, steam or steam injection and hot water and in situ combustion that will increase the temperature of the reservoir. Chemical enhanced oil recovery operations like surfactant that will work to reduce the oil water interfacial tension. Polymer flooding, the concept of this technique is to control the mobility of the injected water. And also we have immiscible displacement like the CO2 injection operation. And we also additionally have the microbial enhanced oil recovery operations. So the primary recovery, as you can see, we have this is the relationship of fluid versus time. This is the typical profile of fluid versus time, as you can see for the primary recovery. After the production buildup, we have this period of the production plateau. After that, we have the specific decline in the production rate, so which marks the end of the primary recovery operation. At this point, the secondary recovery operations can be implemented like water or gas injection operation. After the depletion and decline of recovery by secondary recovery, we may start tertiary or enhanced oil recovery operations. As you can see, the oil recovery versus time can be, we have added value due to secondary and tertiary recovery. In terms of the oil viscosity for light oil, we have up to 25% of the original oil in place can be recovered by primary oil recovery techniques. Up to 30% can be recovered by secondary recovery, and the remaining is can be recovered by enhanced oil recovery operations. On the other hand, for heavy oil, we have only up to 5% of the original oil in place is recovered by the primary recovery operations without any support from external sources to support the reservoir pressure. And for the second recovery, we have additional 5% of the original oil in place, while the about 90% of the original oil in place can be recovered by the enhanced oil recovery operations. So simply, our objective is to maximize the value of the asset of we have or the value of the oil field. So as you can see, this is the typical relationship of cash flow versus time during the different stages of oil field development. We typically have 4 different stages in the oil field operations, starting from exploration, delineation, development, and maturity phase. Within the exploration, the reservoir subsurface understanding is not highly defined, while within the delineation phase, we have the reservoir subsurface structure and reservoir extension is highly understood. So in this case, we have production buildup, as you can see. Within the reservoir in the development stage, we have the production plateau or peak oil production. In this case, we have to extend this period as much as possible. After that, within the maturity phase, we have to work to extend the oil field lifetime by different reservoir optimization operations like water injection or water flood operations. So at the beginning, we'd like to identify the role of water within the oil field operations. As you can see, we have this 3D model of our reservoir. So we are at production wells. We have produced water. So at surface, we have to separate the produced water with the associated with the oil production. After that, the water is diverted to the water treatment. Within the water treatment, for very high volumes of water, the water may be diverted to water disposal or water injection. So the water is available throughout the entire oil field lifetime and entire oil field operations and cycle. We have water during production. So within the subsurface reservoir, the oil is swept by water and displaced by water, maybe naturally like water aquifers or artificially like the water injection. At specific levels, the water may present a problem at surface at higher volumes of water produced with oil. So in this case, the surface water treatment system may be overloaded in this case. The water may be subject to water disposal and water injection after proper and specific water treatment on the surface facilities. Specifically, as you can see, this is the in the detailed model. And within the production, we have specific production profile and producer performance. At surface, we have separation of the produced phases. Let's focus on the water produced water. This water will be subject to water treatment, water disposal, and water injection. And the subsurface reservoir, as you can see, we have injector performance, which is typically dependent of the quality of the injected water. It's a very critical issue in all water injection or water flooding operations. And injection mechanism or injection profile, like the injection from the peripherals of the reservoir or injection according to a specific injection pattern. So water flood is a secondary recovery technique to maximize oil recovery by injecting water as immiscible displacement process. The main objective is to maximize and to maintain the average reservoir pressure, increase the oil recovery, and to supplement with natural water influx. One of the main reasons for the dominant applications of water injection is to availability of water, a relative low cost of water injection relative to other techniques like the chemical or enhanced oil recovery techniques, and the ease of water injection and the availability of injection water and high displacement efficiency that can be achieved by water injection. So typically, the main objective of water flooding is to support the average reservoir pressure as a pressure maintenance operation, displace or push the remaining oil towards the oil production wells. And one of the very important reasons for water flood is to eliminate more gas to release out of the liquid, because in this case, once the average reservoir pressure is declined below the saturation pressure or the bubble point pressure, so we will have the solution gas will start to release out of the liquid phase. In this case, the gas saturation in the pore spaces start to increase. Once the gas saturation is higher than the critical gas saturation, in this case, the gas in the pore spaces will start to move. So in this case, we will have simultaneous flow of oil and gas So we have, in this case, two-phase flow in the porous media. So the relative permeability of oil will decrease. So we have to eliminate more gas to release within the porous spaces to avoid any reduction of the effective or the relative permeability of oil within the porous media. And finally, the important objective is to increase the recovery factor. Typically, the expected recovery factor can be achieved by water injection up to 30 or even 40% of the original oil in place. So how does it work as a water injection or water flood operation? As you can see, we have this model. We have this reservoir bay sand. We have oil production from these oil producers, and this is the source water sand. We have two wells as source well and injector one. So the water will be injected from this injector well. The injected water will be in the peripherals on this reservoir in the down dip of the oil zone, as you can see, while the injected water will displace or push the remaining oil towards the oil production wells to maximize oil production and to minimize the remaining oil in the reservoir. We have, this is the mechanism of water injection, while the mechanism of water flooding, as you can see, we can inject water within the oil zone according to a specific injection pattern. As you can see, we have this five spot pattern. We have this oil producer, and we have four injectors. The four injector, we have 25% for every injector well. So we have injector to producer pattern. This is the movement of the injected water. This is the invaded zone by the injected water. So the water will push or displace the remaining oil towards the oil production wells. So the value of water flood, as you can see in this case, we have three different field cases. The base case is the recovery by the primary recovery techniques, and this is the highlighted in yellow. We have the recovery may be achieved by the optimization of the field operations, while in the green color, as you can see, this is the recovery due to water flooding operations. As you can see, we have significant increase in the incremental oil recovery due to water flooding operations for three different fields, as you can see. We have this is the important value of water flood. So the important of geology in water flooding operations, as you can see, we have two different techniques as primary and secondary recovery techniques. The reservoir continuity and little reservoir changes of reservoir permeability is very important to achieve efficient water injection and water flooding operations. To as you can see, for in this case, we have as a primary recovery, we have influx of aquifer water in the down dip, and we have the expansion of gas cap gas in the up dip, so the reservoir pressure will be maintained as long as we have active displacement from water and gas. On the other hand, as you can see, in this case, we have secondary recovery as water injection. So to have efficient water injection operation, we have to ensure the reservoir is highly extended throughout the injectors and producers to keep the injector to keep the oil producers affected by the injected water and to maintain the average reservoir pressure. So the value of recoverable oil and ranges of different reservoir driving mechanisms, as you can see. For solution gas drive, we have up to 15% of the original oil in place can be recovered. For the gas cap drive, in the optimum situations, we have up to 45%. For natural water drive, we have up to 50%. This is the optimum, and the maximum values can be achieved. However, in the actual field cases, the achieved recovery factors is much less uh, the uh, the expected recovery factors due to different parameters like the reservoir heterogeneity, reservoir extension, other parameters like expand the release of solution gas, the optimization of the production operations, and so on. So the estimation of the displaced oil, as you can see, this equation can be used to calculate how much oil in place can be recovered by the displacement by water flooding operations. It's typically dependent of the original oil, the oil in place at the start of water flood, which is N, and we have three different indicators for water flood performance: the displacement sweep efficiency E sub B, aerial sweep efficiency E sub A, and vertical sweep efficiency E sub V. So the water injection or water flooding operation is typically dependent of the sweep efficiency and oil in place at the start of water flood. So, and very specifically, the parameters that control the water flood recovery. At first, the oil saturation at start of water flood or is sub O, the residual oil saturation to water flood. How much connect oil we have free gas saturation is very critical parameter for water flooding operations. Water flood proof volume is it's related to the oil in place at start of water flooding. The most important fluid properties are the viscosity of oil and water, and also the rock properties or even rock and fluid properties, the effective permeability to oil at the reducible water saturation KO at SWI, and relative mobility to water. And another important factor, which is the reservoir stratification and the reservoir permeability variation, or Dijkstra-Barson coefficient, water flood pattern, and the injection rate, and another fluid and PVT parameter, which is the oil formation volume factor, and finally the economic considerations. So for successful water flood, we have to start water flood as early as possible to eliminate the more gas to release out of liquid. So high gas saturation will decrease the oil recovery by water flood due to we will have high long period of time which is related to gas fill up. The second issue is the well spacing tighter. Well spacing is better, specifically for the low reservoir heterogeneity, and the selection of water injection pattern is also critical to success for the successful of water flooding operations. So the shallower depths are recommended. Low oil energy or low oil formation oil volume factor is preferred to avoid any losses, any mass losses in the produced oil while production, because in case of we have high oil formation volume factors, so we have high volume losses due to release of gas while we have reduction of pressure from the average reservoir pressure to the wellhead pressure. High reservoir permeability is better for water flooding operations because in this case we have low permeability variations, and we may use wider well spacing, which is cheaper in terms of number of injection wells, and also the moderate to low oil viscosity. So the first important aspects related to water flooding is the geological aspects. The most important is to ensure we have low reservoir heterogeneity or permeability contrast between different reservoir units or reservoir layering. And isotropy is also a critical aspect to water flooding. It's related to a maximum and horizontal permeability variations, and typically related to the depositional environments and of the subject reservoir. Drainability, which is related to the production by the primary depletion. It's an indicator for the successful of water flooding operations. So as you can see in this case, we have this sand bodies. We have to ensure good lateral continuity of the potential reservoir between the injectors and the producer. Also, it's important to avoid any structure elements or sealing structure elements like faults between the injectors and producers to avoid good communication between the injection and the producer wells, and to ensure we have good support and efficient support for the average reservoir pressure. So, and to summarize this, for successful water flood, we have to have sound and a good understanding of the geological models to understand the reservoir complexity and the reservoir uh, heterogeneity. Also, in this model, this is the channeling system. So, you have to ensure the communication between the specific channels that will have injectors or producers to control the average reservoir pressure. Now, the important reservoir work aspects, as the most important aspect is the relative mobility data. So at the beginning, let's define the reservoir rock permeability or the absolute permeability. As you know, it's defined by Darcy's law. It's a rock property related to fluid flow. The permeability is typically directional. We have the three terms of permeability in X and Y and Z. The permeability in vertical direction is typically less than the horizontal permeability. The absolute permeability is defined at 100% saturation of the reservoir rock with specific or single fluid. So the absolute or specific permeability is the ability of this rock to transmit this fluid at 100% saturation, or the fluid conductance capacity of the porous media. It's defined according to this equation in the oil field units. While for the effective permeability, in this case, we have more than one fluid in the pore space. So the effective permeability is the permeability to a particular fluid. In case of the porous media is saturated with more than one fluid, like oil and water, or even oil, water, and gas phases. So the applications of relative and effective mobility data, typically reservoir simulation and all fluid flow calculations that include the multi-phase flow equations or multi-phase flow applications in the reservoir. So in this case, we have to apply the effective and relative mobility definitions. So this is the definition of the effective mobility to oil and water and gas as defined by Darcy's law. So the relative mobility in this case, we have two or more than two fluids flowing simultaneously within the porous media at the same time. So the relative permeability is defined as the ratio of the effective permeability to a particular fluid at a given saturation to a base permeability. You have to know as we have two common base permeability. The first is the absolute permeability or the air permeability. The second and commonly used base permeability is the effective non-wetting phase permeability at the irreducible wetting phase saturation. In other words, it is the key, the effective permeability of oil at the irreducible water saturation KEO at the value of SWI. So this is the typical shape of water oil relative permeability curve. As you can see, we have the increase in water saturation in this direction, and accordingly, the relative permeability to water will increase from this point as reducible water saturation to reach at this level KRW at SOR. And the other in the opposite direction, we have the in this direction we have increase in oil saturation. So the relative mobility to oil will increase from this level, from this point to reach 100% or one at a reducible water saturation, which means we have the base permeability in this case is K, the effective permeability to oil at SWI. So at this point, the relative permeability to oil will be 1 or 100%. So you have to know we have different endpoints for any relative mobility curve. Typically, four endpoints. The first endpoint is this point is the reducible water saturation is WI, and residual oil saturation is OR. And the for relative mobility, we have relative mobility to oil at SWI and relative mobility to water at SOR. Within this region, we have, as you can see, we have single phase flow in which is oil flow, and within this region, we have single phase flow, which is water flow, while in between we have two phase flow region. As you can see, this is the importance of relative mobility data for different rock types. The relative mobility is typically dependent of the reservoir quality and the reservoir fishes distribution. So as you can see, we have two rock types. The recoverable oil for rock type 1 is higher than the rock type 2 as a function of pore volume injected, because in this case, the rock type 1, we have the value of KRO and KRW, the value of intersection between the two curves is located at higher water saturation, which means we have a strongly or water wet rock. In this case, the expected recovery from water flood operation is expected to be high relative to oil wet reservoirs. So the water relative mobility data relative applications, typically the any multi-phase flow calculations in the reservoir, and typically for water flooding operations, we have to use water oil relative mobility curves. Typically, the factors affecting relative and effective mobility data are the fluid saturation and pore geometry, rock wettability, and fluid saturation history in terms of imbibition and drainage. Typically, this is the effect of wettability. As you can see, the strongly oil wet rocks. In this case, we will have the value of KR, the value at which KRO at equal TRW at this point A appears and located at a value of water saturation higher than 50%. As you can see, the water saturation of this point is higher than 60%. This is the first indication, and the second indication is the value of SWI. In this case, we higher value of SWI higher than 20%. While for strongly oil-wet reservoir and oil-wet rocks, the SWI is less than 15%, and the point of intersection between oil and water relative mobility curves is located at water saturation more or less 50%. So in this case, the at this point, the relative mobility of oil is equal to the relative mobility of water. The next is and very important effect is the effect of saturation history. Typically, the imbibition curve, in this case, the wetting phase saturation will increase. So we have the non-wetting phase like oil is displaced by the wetting phase. It's a typical water flooding process in a water wet reservoir. While so this is, as you can see, this is the typical shape of the imbibition curve. We have increase in the wetting phase saturation and this one. While for drainage, we have increase in the non-wetting phase saturation. In this case, the wetting phase uh, saturation is decreasing. It's a simulation process for the migration of oil through a gas cap into the reservoir. So as you know, the all reservoirs are initially saturated with 100% water. So within migration, so the oil or gas will displace the water to form a drainage process. It's important to know we have to normalize and to make normalization and averaging for relative mobility data to for applications of water flood. As you can see, we have laboratory data for different curve logs. This is the water oil relative mobility data, laboratory data. The next step is to make smoothing of this data, as you can see. The next step is to make the average normalized data to make this type of relative mobility curve. And the last step is to make the denormalization of data and compare the denormalized data with the originally measured laboratory data. So for applications of water flood, we have to use relative mobility curves. But before this application, you have to make normalization and averaging of the relative mobility data to start applications of water flood calculations and immiscible displacement calculations. The next important issue or factor related to the reservoir rock is the rock potability. It's typically the tendency of one liquid, for example, oil or water, to spread over the solid surface or the rock surface. In case we have more than one fluids are located in the pore spaces. So in hydrocarbon reservoirs, you know, the rock surface may be different sandstone or carbonate reservoirs. And for waters, for the liquid, we have water and typically oil. So it's important to highlight the most reservoirs is typically ranges from strongly water to oil wet or even neutral wet. So the common measurements of rock wettability are two techniques: the contact angle test and amode wettability. So this is the classification of rock wettability based on the contact angle. we have two different types, may be oil wet and water wet. So I will not go through in details in this section, just to highlight the definitions. As mentioned before, we have two different techniques. We have infusion, so like water injection or water flooding operations in oil reservoirs. Uh, in case of the reservoir work is water wet. So in this case, we have increase in the wetting phase saturation or the increase in the water saturation. While on the other hand, the drainage process is the increase in the non-wetting phase saturation, like gas injection in oil, in an oil or water wet oil reservoir. Now it's important to highlight the effect of wettability on the oil recovery. So for strongly water wet, we have higher oil recovery before the water breakthrough, as you can see from this plot. While after the water breakthrough, we have very small increase in the oil recovery, because in this case we the water will start to move faster than the oil. While for oil, strongly oil with rocks, the oil recovery will be lower before the water breakthrough. But after the water breakthrough, the oil recovery will gradually increase, as you can see, because in this case we have more water is produced from the reservoir, so the mobility of oil will increase with time. The last important rock property is the Kepler pressure. You know, the Kepler pressure is the difference existing, the pressure difference existing across the interface separating two immiscible fluids like water and oil. By definition, the Kepler pressure is the pressure difference in the non-wetting to the pressure minus the pressure in the wetting phase. This is the typical Kepler pressure curve, and it's based on the fluid distribution and in the reservoir. So as you can see, we have the x-axis. We have water saturation. At this point, we have the free water level at which the Kepler pressure is zero. Starting from this point, which is the displacement pressure. So this is the pressure required to introduce the non-wetting phase into a initially wetting phase saturated pool. So this is the shape of Kepler pressure will follow this trend until the irreducible water saturation at this level. So this area in between this the start of displacement pressure to the reducible water saturation, this height will control the transition zone between the oil and water. So in this region we have 50% 100% water or free water, and within this region we have free oil, and in between we have the transition zone. So the thickness of the transition zone is typically dependent of the value of the Kaplan pressure. So to highlight this, we have two oil and water gradient, and the point of intersection between the oil and water is the free water level, at which the Kepler pressure equals zero. And we have above the free water level, we have specific transition zone, as you can see, based on the value of Kepler pressure and based on the reservoir pore size distribution. So as you can see, higher the pore throat, we will have very low transition zone, while for very low post-throat radius, the capillary, the thickness of the transition zone will be very high, and the capillary pressure will be higher. So this is the typical applications of the capillary pressure is to identify the initial saturation and the fluid distribution in the reservoir. Typically, as you can see, this is the we have gas zone, and below we have this oil zone, and at this level we have the oil water contact or the free water level at which the capillary pressure equals zero, and the thickness of this the transition zone between oil and water is dependent of the capillary pressure and the density difference between the oil and water according to this equation of the capillary pressure. So to highlight this again, this is the typical shape of the capillary pressure curve. Also, the capillary pressure is dependent on the fluid saturation history, maybe the drainage or imbibition. So the for the imbibition curve, we have increase in the wetting phase saturation at this point, which is the residual non-wetting phase saturation. While for this green curve, we have decrease in the wetting phase saturation, so we have drainage process. So the shape of the capillary pressure curve will be dependent on the fluid saturation history. Just to highlight the effect of reservoir mobility of the capillary pressure curve, so as you can see, we have this core data for different core blocks. So as you can see, the value of the capillary pressure curve will be related to the reservoir mobility, such that the higher reservoir mobility will the capillary pressure curve will shift to the left, which means we have very low the transition zone, and
So thank you, sir.
pressure is the related to the value of reservoir mobility. So a higher reservoir mobility, like this curve in the black color, we have lower thickness of the transition zone and very low value of the SWI. While for the red colored capillary pressure curve, the value of mobility is much lower. So we have higher initial water or reducible water saturation, and we may have more high thickness of the transition zone between oil and water. So for averaging the capillary pressure data, we have a very important technique, which is Lipid J function. J function is typically a technique to develop a universal capillary pressure curve. J function is the dimensionless function that relates the capillary pressure with reservoir rock and the fluid properties. So it's the definition of the J function. It's related to the capillary pressure, K reservoir porosity and permeability, and the interfacial tension and contact angle between the fluid and rock surface. So this is the J function, for example, for a case history field. So it's an averaging technique to for the capillary pressure data. This is another example to use the averaging capillary pressure data. We have different core blocks, and this is the applied the average capillary pressure curve by after normalization of water saturation to account for different values of SWI. So another important issue to consider, we have different laboratory techniques for capillary pressure. We have mercury injection and centrifuge method or stored state method. What's important to know is we have to convert the capillary pressure data measured at lab to equivalent reservoir conditions according to this relationship. Just as summary for capillarity and wettability effects, the capillarity is typically dependent of the interfacial tension between oil and water, wettability effects, and both road size distribution. So higher, large both road size, which in this case we have lower capillary pressure and the more water oil transition zone. Now I'd like to highlight the reservoir heterogeneity. Reservoir heterogeneity, as you can see, it's related to the uh, the distribution of reservoir properties laterally from between injectors and producers. So in water flooding, you have to avoid any structural elements like the sealing faults between this injector and this producer. So if we consider water injection from this well in layer 5 and layer 6, so this oil producer will not affected by the injected water because we have this sealing fault between them. So for efficient water flooding operation, you have to ensure no structural elements. You have to ensure good lateral distribution of the reservoir between injectors and producers. So in the layer, there is a variation or heterogeneity between layers. So we have two different techniques to identify the permeability variations. The important one is the Dijkstra-Bowson coefficient to calculate or to identify the permeability variation before always in designing water flooding operation. And the second is Lorentz coefficient of heterogeneity. I will highlight very quickly the Dijkstra-Bowson. It's a coefficient of probability variation is defined. It's defined by this equation. It's an equation of function of probability at uh, K50 and K41, 84.1 and K50. So K50 is the mean permeability or probability value at 50% of the cumulative sample distribution. So the procedure of the Dijkstra-Bowson is to store or sort your probability data in decreasing manner and calculate K50 and K at uh, 84.1% of the cumulative sample distribution. In this case, you will find a relationship like this. And according to this relationship, we'll highlight or identify the permeability variation. So the Dijkstra-Bowson ranges from 0 to 1 or 0 to 100. So 0 means we have completely uniform reservoir or homogeneous reservoir, while for values of Dijkstra-Bowson at or more or less one. So we have in this case completely heterogeneous reservoir, which is not recommended for water flooding operations. This is the example to calculate the Dijkstra-Bowson. As you can see, we have this relative mobility data. We can plot this relationship. We can sort our mobility data in this curve of the Dijkstra-Bowson. So we have the relationship between the effective mobility at SRI to absolute mobility. In this case, as you can see, the effective mobility is much less than the absolute mobility or Bowson coefficient. as a function of permeability and cumulative probability. So now the definitions of mobility and mobility ratio. Mobility is simply the ratio of effective permeability to the viscosity of a specific fluid. So mobility is permeability of the rock to a specific fluid relative to the fluid viscosity. Typically, we have this definition of mobility of water and oil. So this is the mobility of water. It's ratio of kW over mu w. In terms of this is the effective mobility to water. So it can be represented by K absolute times R W, or the relative permeability to water. For oil, we have similar definition of the oil mobility. So the mobility is a very critical parameter for successful water flooding operations. We have to ensure we have lower water mobility and higher oil mobility. So as the second important definition is the mobility ratio. As you can see, the mobility ratio is simply the ratio of mobility of the displacing phase to the displaced fluid, or the mobility of water to mobility of oil. It will follow this definition. So for water flooding, it's important to keep the mobility ratio less than 1 to ensure the efficient water flood and higher oil recovery. So for mobility higher than 1, we have unfavorable mobility ratio. In this case, the water will move easier in the reservoir relative to oil, which is not recommended in water flooding operations. In this case, we may apply the flooding operations to control the mobility of water, while foil mobility is less than 1, which is a favorable mobility ratio. In this case, the oil will flow more easier than the formation water, which is highly recommended in water flooding operations to ensure maximum oil recovery and delay the water breakthrough. So recovery process in typically in field operations, we have 5 different reservoir driving mechanisms, as you can see, from solution or gas cap drive, water drive combination, and gravity drainage. We have different sources of reservoir energy, like expansion of and release of solution gas, expansion of gas cap gas, influx of aquifer water, and even we have gravity effects on recovery. So the optimum solution is to combine the depletion with the displacement. As you can see, like the solution gas drive with the water injection. In water injection, we have 2 different scenarios, bottom flood and down dip peripheral injection. So the favorable of maximum oil recovery in case of gas cap drive reservoirs is to we have large ratio of gas cap to oil zone, or large gas cap size. For water, in case we have large aquifer or high strength or strong aquifer, it's preferred to maximize oil recovery. Or in this case, the water flood, in case we have strong aquifer, the water flood operations may be neglected due to we have higher reservoir energy. For gravity drainage, we in case we have high dipping in the reservoir is favorable, and high and large reservoir fluid or density difference between the oil and water is also recommended to maximize recovery by gravity drainage. So the common negative factors related to water flood, we may have different not recommended issues relating to water flood, like low production rates related to low reservoir pressure or low reservoir energy, poor hydraulic conductivity, and also for injection we may have poor hydraulic conductivity. Also, one of the negative issues for water flood is the early water breakthrough, which is related to high permeability contrast between the reservoir layers. Also, corrosions and scalings and plugging problems related to water injections operations is also one of the negative issues related to water flood. So, however, we have different negative issues of water flood. The water flood is or the most widely used secondary recovery technique. Now, I will highlight the definition of the voidage replacement. The voidage replacement or voidage replacement ratio is the ratio of injection to production ratio for a specific pattern or even throughout the field wide. The reservoir voidage is the summation of reservoir oil and water and gas production calculated at the reservoir conditions. In this case, we have to consider the free gas production in case we have the average reservoir pressure is lower than the saturation or bubble point pressure. This is the definition. So voltage replacement ratio is the summation of water injection on even water influx divided by the reservoir voidage. So reservoir voltage is defined by this equation: oil plus water plus free gas production converted to reservoir conditions by multiplying by the formation volume factor of oil and water and or gas. So the voltage replacement ratio, as you can see, it's the ratio of the water injection, total water injection to the total reservoir voidage. So in successful water flooding operation, it's important to keep the voltage replacement ratio higher than 1 to keep the average reservoir pressure more or less constant, while for the voltage replacement ratio lower than 1, so in this case the reservoir pressure will steadily decline due to we have depletion in the average reservoir pressure. Typically, we have different reasons for the pressure losses while water injection due to the reservoir heterogeneity, due to gas or solution, gas or free gas fill up, poor communication between and poor sealing, and even we may have leakage faults. So in this case, we will have losses in the injected water. Generally, we have from 20 to 30% lost in the injected water due to reservoir heterogeneity parameters. And now I will highlight the miscible displacement process in a porous media. So for water flooding in operations or water flooding is typically an immiscible displacement process. It's typically governed by three fundamental concepts started by the fractional flow equation developed by Leverett in 1941. The second one is the frontal advance equation developed by Buckley and Leverett in 1942. Tangent method of analysis of the fractional flow curve developed by Welch in 1952. So this is the fundamentals of miscible displacement and applications of water flood. They will be used to identify the ground stability and peak through time and even the sweep efficiency of water flooding. So this is the definition of the fractional flow. It's the important model used to identify the water fraction relative to the total flow at a particular location and time in the linear reservoir model or reservoir or water flood system. So the fractional flow, as you can see, is a function of the mobility ratio and the mobility and gravity and capillary terms. So the fractional flow will provide important insights related to the immiscible displacement process and the water saturation distribution within water flooded zone. So in this equation, as you can see, we have two important parameters related to gravity term, which is function of the dipping of your reservoir and the difference between oil specific gravity and water, or the density difference between water and oil. And the second term is the capillary term, which is related to the capillary pressure effect. And generally, in fractional flow applications, we will ignore the gravity and capillary terms to apply the fractional flow equation. Typically, for fractional flow of water, as you can see, if we have a higher fractional flow, so in this case, we have 100% water flowing in the reservoir, which means no oil flow, which is not recommended in water flooding operations, while a low fractional flow of water or low water cut means efficient water injection or water flooding operations. So the fraction of water flowing at any point in the reservoir at point X in a linear water flood system is defined by the fractional flow like this. In terms, the second gravity term in this case, this is the function of the density difference between oil and water, and this form is the function of the specific gravity difference between oil and water. So the fractional flow is typically a relationship of different fluid properties like viscosity and density, rock property like the effective permeability and saturation, total throughput rate like the injection rate, pressure gradient or the capillary pressure, and structural property like the dipping of the reservoir, which is the parameter alpha. So in case we have the water injection with the up depth, so this will improve the efficiency of water flooding operation due to the gravity effects. So this is the to flow the flow at any location in the reservoir is defined by this equation. The total reservoir is defined by Q oil and Q water. So the fractional flow simply equals Q water by Q oil plus Q water or Q water to Q total. So the fractional flow of water is the fraction of water flowing in the reservoir relative to total fluid flowing in the reservoir. So for highly efficient water flooding operations, so we have to keep the fraction of water flowing at any location in the reservoir as a minimum as possible to maximize oil recovery. This is the simplified form of the fractional flow in case we have horizontal reservoir, so we have no dipping effect, and by ignoring the capillary and gravity forces, so this is the definition of the fractional flow equation. The fractional different forms of the fractional flow uh, can be related to the water or ratio according to this definition. So Q water relative to Q total, it's the function of water or ratio at reservoir conditions. So we have different forms of the fractional flow equation. So the controls of the fractional flow, the reservoir dipping is very important. So up dipping displacement of oil by water or up dipping water flood will improve the efficiency of water flood due to the gravity forces. Also, in case we have large density difference between the water and oil, also will improve the water flood efficiency. Typically, the fractional flow curve is dependent of wettability and dipping and the oil and water mobilities, as you can see. So the high mobility oil like this, we have the fractional flow of water will be higher, which is not recommended. And also for down dipping displacement, it's on injecting up dipping displacement is recommended to improve the water flood efficiency and reduce the fractional flow of water. So also the relative and effective mobility has effect on the fractional flow because this equation is simply function of the relative mobility of oil and water. The fractional flow is a function of water saturation. It's a very simply and it's related to the relative mobility data as a function of water saturation. So for to discuss the displacement theory in water flooding operations, so we have immiscible displacement. We consider this model as a linear 1D model between this injector and this producer, and we have specific reservoir property where the developed models are dependent of different assumptions. One of them, the gas saturation is zero and the condensate water saturation is immobile. So this is the one of the widely and initially used techniques for displacement or miscible displacement is the piston-like displacement model. It's a very ideal model. As you can see, the water injected from this side. We have, as you can see, the condensate water, the minimum water saturation, and from this side we have water injector, and from this side we have oil producer. So, and at this location we have the flood front. So the oil saturation at the flood front is the difference between 1 and SWI. And behind the flood front, we have the oil, residual oil saturation in the water flooded zone. This model is very ideal and very simple to discuss the displacement theory. So the modification of this model is the leaky piston model, as you can see. So this is the injected water bank, and we have this minimum water saturation or the condensate water saturation. And within this is the initial oil saturation, as you can see, the flood front is not uniform. It's very very related to the actual injection operations. So in this case, water displays oil in manners related to the not uniform water flood front. and the remaining oil is swept by the injected water moving behind the flood front. In case we have a specific trapped gas or injection below the saturation pressure or the bubble point pressure, so as you can see, this is the distribution of saturation or water saturation between this injection side and this production side. So water flow in this case, we have this water bank towards the water injector and the oil bank, and then you have, in this case, the water flood response will be delayed due to the presence of initial free gas in the reservoir, and the response of water flooding will be delayed due to the time for gas fill up to compress the free gas in the reservoir and to keep or to mix the free gas to back into the solution again at a higher injection pressure. So why we don't have this like effect? Because we have gravity effects. So when we have gas on free gas in the reservoir, when we have permeability variations or areal heterogeneity, also we may have fingering of the lower, higher mobility water. Also the relative permeability and the fractional flow will not be as homogeneous. So this is the ideal displacement process, and while this is the actual displacement process as a relationship between hydrocarbon recovery as relative to the cumulative bulk volume water injected. So the next important definition is the frontal advance equation. This equation is important to identify the saturation distribution of different phases at any time while water flooding. So the frontal advance equation is used to calculate the water saturation in the water embedded zone of the linear system or the subsurface reservoir. This is the definition of this equation. So this is the x, the distance between the from the injector. So water saturation will be calculated at time t and distance x. The value of IW is the injection rate, and the T is the time interval in days from start of water injection, and W sub I is the cumulative water injected at the calculation time T. So this equation is very important to identify the water saturation distribution within the linear displacement system or water flooding operations. So typically we have this ideal reservoir linear system between this injector and one producer. On this side we have water zone, and towards the oil producer we have oil zone. This is the initial saturation distribution, as you can see, and this is the water saturation from 0 to 100. So next, in the water injection side, we have the water saturation following this trend. So this is the average water saturation behind the flood front. This is the flood front, and this is the water saturation at the flood front. While this is the injection side, we have the minimum water saturation with the connect water saturation. So this is the typical the saturation distribution for the miscible displacement process calculated by the frontal advance equation. So at different times, as you can see, this is the shape of the saturation distribution and the location of the flood front at this time, and at time one and at time two, which is the time of peak flow. So as you can see, the flood front is located at the production well. So this technique of which is the solution of the frontal advance equation, is very useful to calculate the displacement efficiency and calculate the time, fixed flow, and water saturation at the flood front and water saturation at the peak flow. This is the derivation of the this method. I will not go through in details of this section. So what's important is to know the frontal advance equation I mentioned before. This equation. So the frontal this equation will be used to calculate the water saturation at time t and distance x from the injector. So what's very important in this section is to identify this technique of the Welch solution, which is graphical solution. So as you can see in the blue color, we have this fractional flow curve. This technique is to plot this straight line from the reducible or coordinate water saturation and take this the tangent of the fractional flow curve. At the tangent point, we have this this at this point. Typically, we have the water saturation at flood front and the fractional flow at the flood front in the y-axis. So at fractional flow equals 1, we have the average water saturation at peak flow at this point. So this technique is very useful to calculate the average water saturation at flood front and water saturation at peak flow. Accordingly, we can calculate the displacement efficiency of water flood. So water flood performance efficiency, this it will calculated by this equation. It's related to the displacement, areal and volume, and the vertical sweep efficiency times the oil in place at the start of water flood, and in ND is the oil cumulative oil production due to water flood. So the oil in place at the start of water flood, it's a function of the flood bulk volume and oil saturation at start of water flooding operations. Aerial sweep efficiency is the fraction of reservoir area contacted by the injected water. Vertical sweep efficiency, if we consider the vertical plane of the between injection and production well, so we will calculate the vertical sweep efficiency. For the displacement efficiency, is the fraction of oil which will be displaced by the injected with the injected water. So, and very simply, this is the relation of the aerial sweep efficiency. It's the relation, the ratio of the invaded the area invaded by water to the total pattern area. If we consider this flood pattern between this injector and this producer. This is the changes of the aerial sweep efficiency with time. So as you can see at this point, we have this efficiency. We have aerial sweep efficiency about 65% for this case, while at the end of water flooding operations, we have aerial sweep efficiency up to 96%. And as you can see, we have a linear relationship between the aerial sweep efficiency and the water oil ratio. So the water oil ratio will significantly increase at even before and after within the breakthrough at this point, and we will have higher increase in the water oil ratio after the breakthrough. As you can see, we have in this case water oil ratio is 4.7. So for the vertical sweep efficiency, if we consider the vertical plane, the vertical sweep efficiency is the vertical cross section contacted by the injected water. So generally, the water flood efficiency is the cumulative production can be correlated with the oil in place at start of water flood and the recovery efficiency of water flood. This term is the aerial and vertical times displacement efficiency of the water flood. Also, to calculate the displacement efficiency, we can use this equation, which is the average water saturation at flood flow um, minus the reducible water saturation to relative to 1 minus SWI. So using the fractional flow curve, we can calculate the displacement efficiency of the water flood. So we can consider this example of we have this fractional flow curve, taking this line from the SWI or SWC, and taking this line as the tangent point. We have the water saturation at flood front about 55%, and fractional flow or water cut reservoir water cut at flood front about 82.5%. To get the average water saturation in the reservoir at the flood front, we will take the point at FW equal 1. So in this example, the average water saturation at flood front is 33% this value. So we can calculate the displacement efficiency according to this relationship, which is about 54%. This is another example. So at the end of this session, I'd like to highlight very quickly a case history of water injection operations. We have a specific field with this is the reservoir rock property data and the reservoir fluid data. We have light oil reservoir. This is the KFI relationship, the porosity and durability relationship. As you can see, we have 4 rock units or hydraulic units of this reservoir based on the relationship between permeability and porosity data. This is the relationship of pressure. This is the oil water contact, and at this level we have the initial reservoir pressure and we have the bubble point pressure. So the reservoir, the average reservoir pressure at start of water flood is lower than the bubble point pressure. So we'll have time for gas fill up to get response of water flood. So the laboratory testing or screening experiments required for water flood are the capillary pressure, which is most important, permeability and wettability data, and also fluid and fluid rock compatibility testing. So this is the capillary pressure data for this example. We have change in reservoir permeability, so we can calculate the averaging of capillary pressure data. And this is the relative permeability data after averaging and denormalizing of data. And this is the end point of this curve. This curve in the green and the blue is the average pre-normalized capillary relative permeability curve will be used for calculations of the fractional flow. And this is the fractional flow curve calculated by the relative permeability data. So we have average water saturation at peak flow about 70%. Water analysis for the we have specific source and formation of water will make compatibility between for the source and formation water, and this is the water composition. For fluid compatibility testing, we have to make compatibility testing to identify the precipitation of the different scales like barium sulfate and calcium carbonate and strontium sulfate, which is the most important scales maybe precipitated during water flooding operations. This is the fluid compatibility testing. So we will monitor the precipitation, for example, for barite or barium sulfate at different conditions of percentage of the injected water. So we have water at this group. We have the injected water is 0%, while in this for this group we have 100% injected water. Similarly, for other component and scales like strontium sulfate and ferric hydroxide, the for fluid compatibility testing, it's an injection or mixing testing between the formation and the injection water at different mixing ratios and different reservoir the injection rates. So we have three formation and injection water mixing ratios like 80 to 20, 50, 50, and 20, 80. This is the ratio between formation to injection water. The purpose of this test is to calculate the effect of the injected water on the reservoir permeability, how we can find the damage or reduction in the reservoir permeability at higher percentage of the injected water. As you can see in this case, at 80% or at 80% injection water, we have higher reduction in the reservoir permeability up to 88%, which means this is the maximum damage can be achieved, can be obtained by the injected water. So generally, for damage less than 20%, so it's acceptable. Damage can be occurred due to water flooding operations. So this is the compatibility conclusions. The most important scales are calcium carbonate and barium sulfate. So in this case, we have to use a specific scale inhibitors to avoid any precipitation of calcium carbonate and barium sulfate within the pore spaces and during the water flooding operations. Also within for water flood designing, it's important to make injectivity or step rate testing. It's a relationship of the injection bottom hole pressure versus injection rate. So as you can see from this test, we can identify the fracture pressure. So we have two pressure pins, and between the intersection between them, we have the fracture initiation pressure. So we have to keep the injection rate for the matrix injection less than the fracture initiation pressure. And for the fracture injection, if we need to make the initial the injection pressure higher than the fracture pressure, we have to inject at higher pressure, higher than this value. For water flood facility and field operations, we have different equipments related to pumping system, high and low pressure pumps, tanks, settling and storage tanks, chemical injection pumps for injecting the scale inhibitors, and finally filtration unit to ensure higher quality of the injected water. This is a samples of the injection facility, pumping system, chemical injection skids, filtration units, and storage tanks. So most important is the filtration unit to remove any solid or suspended solid within the injected water, and the chemical injection to make the use of the scale inhibitors like corrosion inhibitors and biocides or scale inhibitors for to eliminate the precipitation of calcium carbonate and barium sulfate in the subsurface reservoir. And this is the assembly of arrangement of water injection facility in the field. This is the suction storage tanks. After that, we have filtration pumps and filtration tanks before the booster pump. And before in the injector, directly before the injector, we have high pressure triplex pump to provide the injection, the required injection pressure. This is the quality control for the water, the injected water in terms of the suspended solid and water turbidity values to avoid any formation damage. So to summarize this session, the promising reservoir fluid, reservoir water flooding conditions, homogeneous reservoir are preferred. High reservoir porosity and mobility is very promising for successful water flooding operations. Water wet rocks, low oil viscosity, high average reservoir pressure, which is very highly recommended to avoid any free gas in the reservoir. Also, low initial water saturation in oil column is very promising, and availability of the injection water is also recommended to ensure the more reliable water injection operations. So I will just highlight this slide to control the water injection evaluation. As you can see, we have this Hall coefficient to calculate to identify the injectivity problems. And this relationship, if this relationship go to the right, so we have low distance to flow or high injectivity index, which is better for water efficient water flooding operations. So in this case, we have low resistivity or high injectivity index. Also, to calculate water flooding incremental recovery, as you can see, we have about 40% for this case. Annual decline in the production rate before starting of water flood, while within start of water flood after a period of start, we have about 26% annual decline in the annual production. So it's very promising. Also, to calculate the incremental oil recovery due to the water flood. This is the difference between this scenario and this scenario. That's all I have. This is the conclusion of this session. The water flood is widely used secondary recovery technique. Reservoir heterogeneity is a critical aspect of water flood. Relative permeability and wettability are significantly affecting water flood performance. The mobility control is a very important issue to avoid early water breakthrough. Voltage replacement ratio is required to be higher than 1 to maintain the average reservoir pressure as high as possible. For application of the displacement process or displacement theory calculations, we have to make normalization and averaging of the relative vulnerability data to apply the fractional flow calculations. And finally, water flood recovery is dependent on the oil in place at start of water flood and the aerial, vertical, and displacement sweep efficiency. Okay, that's all I have in this session. Thank you so much for joining